From the sour tang of a lemon to the soap you use every single day, our world is basically shaped by this constant, invisible chemical dance. So today, we're going to pull back the curtain on the three key players in that dance: acids, bases, and of course, salts. Okay, let's jump right in.
So, let's start with a little riddle. What on earth could a lemon and an ant sting possibly have in common? I mean, they seem totally unrelated, right? Well, it turns out they share a really powerful chemical secret. Any ideas?
And yup, the answer is acids. That's the connection. The sourness that makes you pucker up when you bite into a lemon, that's citric acid. And that sharp burning sensation from an ant sting, that's from something called formic acid. They're in the same chemical family, but boy, they create very different experiences. All right, so this brings us to the two main characters in our story today. And to really get to know them, we're going to start with something super simple, something we all understand, our basic senses of taste and touch.
Meet our chemical duo, acids and bases. On one side, you've got acids. They're the sour ones. Think of that sharp tang from a lemon or vinegar. And on the other side, we've got bases. They tend to taste bitter, kind of like unsweetened chocolate. And in terms of feel, well, acids can be corrosive, while bases feel slippery or soapy to the touch.
But what's really going on under the hood here? I mean, what really makes an acid and a base a base? To figure that out, we've got to zoom way in and look at their chemical personalities on a molecular level.
So, what's an acid's secret identity? It all comes down to one thing: what it does in water. When you dissolve an acid in water, it releases a positively charged hydrogen ion, which we call H+. That one little action is the source of all of an acid's powers. And bases? Well, they're the total opposite. If an acid is a hydrogen ion donor, a base is a hydroxide ion producer. In water, it creates these negatively charged hydroxide ions, or OH-. These two ions, H+ and OH-, they are perfect chemical enemies.
Let's just put them side by side for a second. So the key takeaway is acids are all about that hydrogen ion, H+. Bases are all about the hydroxide ion, OH-. And this fundamental difference gives us a super simple way to tell them apart: the good old litmus test. An acid will turn blue litmus paper red. A base does the exact opposite, turning red litmus paper blue. For the rest of this chat, just think red for acid, blue for base. Simple.
Okay, so we've met our two chemical rivals. Now for the main event. What happens when these opposites finally meet? This reaction is, no joke, at the heart of everything from the antacid in your medicine cabinet to the cake you bake in your kitchen. It's called a neutralization reaction. Let's break it down. So the acid is in water, releasing all its H+ ions. The base is over here, releasing its OH- ions. You mix them together, and what happens? The opposites attract. The H+ and the OH- ions race toward each other and combine to form, you guessed it, neutral water, H2O. So what's left behind from the other parts of the acid and base? A totally stable new compound that we call a salt.
You know, this quote from our source material just nails it. It's a complete reaction. All those aggressive, reactive properties of the acid and the base, they just vanish. They cancel each other out, leaving behind two perfectly harmless, stable things: salts and water.
I love thinking of it like a chemical handshake. The acid and the base, they reach out, they shake hands, and in that moment, they completely neutralize each other's extreme personalities. They just settle down into this calm, stable partnership of water and salt. Pretty cool, right?
So we know acids and bases are different, but there's a huge difference between lemon juice and, say, battery acid, right? You can drink one, but you definitely don't want to drink the other. So how do we actually measure that difference in strength?
And that's where the pH scale comes in. Think of it like a chemical scoreboard that runs from 0 to 14. The lower the number, the more acidic something is. The higher the number, the more basic it is. And right in the middle, at 7, that's perfectly neutral, like pure water.
Okay, let's make this real. Check out the pH of some stuff you see every day. The gastric juice in your stomach is incredibly acidic, down there at a pH of 1 or 2. That's how it demolishes your food. On the flip side, something like milk of magnesia is a pretty solid base, up around 10. And look at human blood. It's kept in this super tight range, just a little bit basic, around 7.4. If that number changes even a little, it can be really dangerous.
So, how does all this chemistry actually show up in your life day to day? You might be surprised just how often you're using acids and bases without even thinking about it.
So why should you even care about pH? Well, it matters a lot. It's absolutely crucial for our biology. Our bodies are basically complex pH balancing machines. It's essential for growing our food because plants are super picky about their soil. And as you'll see, it's the secret behind a lot of first aid and hygiene tricks. Let's go back to your stomach for a second. That crazy strong hydrochloric acid is a food-digesting superhero. But sometimes your body makes a little too much, and you get that awful feeling of heartburn. So what do? You pop an antacid, which is really just a mild base, and it performs a neutralization reaction right there in your stomach to give you relief. It's chemistry to the rescue.
Want a couple more quick-fire examples? A bee sting hurts because it's acidic. The solution? Put a little paste of baking soda, a mild base, on it to neutralize the sting. And after you eat sugary stuff, bacteria in your mouth produce acid that causes tooth decay. Toothpaste is basic for that exact reason, to neutralize that acid and protect your teeth.
And it doesn't stop there. This chemistry is literally on your plate. Farmers have to be expert pH managers because different plants need different conditions. Rice, for instance, actually grows best in soil that's a bit acidic, while a lot of fruit trees prefer soil that's more alkaline or basic.
You know, when you step back and look at the big picture, this quote really says it all. This constant balancing act, this dance between acids and bases, isn't just some abstract concept from a chemistry class. It is absolutely essential to life as we know it.
All right. We have covered a ton of ground. We've learned that salts are these nice, stable, neutral things that are left over after the big reaction. But what if I told you that some salts have a bizarre superpower? They can actually pull moisture right out of the thin air and completely dissolve themselves. So what's the deal with that? Now that is a great question to chew on. Thanks so much for watching.